Hello, my name is Jay Kashyap, and this is Lab 1 on constant velocity for Physics 2211. So, in this lab, we'll be observing the position of a marker rolling across a table at a constant velocity and comparing it with a computational model of the marker's predicted position. So, a couple fundamental principles that are involved in this lab. So, Newton's first law says that an object in motion stays in motion with the same speed and direction unless acted upon by some net force. And then Newton's second law says that a change in momentum means that there is a net force. What we can take from this is that when the net force acting on an object is zero, constant velocity is achieved. This is because the net force is zero, which means the acceleration is zero. So velocity will not change. This equation is called the velocity update formula, and it's given by the final velocity is equal to the initial velocity plus the net force divided by the mass times the change in time. However, in our situation, when the net force is zero, the formula just becomes the final velocity is equal to the initial velocity. Okay, so now I'm going to show the video of the marker. So that's what we're using for our data. Alright, so here, it's a piece of code for the computational predictions. This first part here, the mass of the ball, it doesn't actually matter in this case because the net force is zero. The initial conditions was that the position vector starts at around 0.0491, and then the velocity is initially 0.413, and that was calculated using the final position and the time. So that's what our initial velocity was. And then here, the size of each time step is 0.033 seconds. Alright, so this is another piece of code. You can see here that the net force vector is all zero. So to ensure that the velocity is constant and there's no acceleration. This is the velocity update formula written out. The velocity of the ball is equal to the initial velocity of the ball plus the net force divided by the ball's mass times the change in time. Since the net force vector is zero, this entire part of the equation gets canceled out, and the velocity is just equal to itself. The position is just simple velocity times the change in time to get that displacement. And this is all just plotting and advancing the clock. Okay, so here's a graph of the computational prediction of motion. As you can see, it is a straight line, linear for the position, and the velocity is a completely horizontal line, which indicates that the velocity is constant and that there's no acceleration. So this is the comparison of the observed versus the predicted position. As you can see, they're pretty different, and there are a couple factors that could lead to this, such as like friction, all those kinds of things that could have led to the difference in observed versus the actual model prediction. So how would your results change if you were to flip the axes? The only way that they would change would be that the position graph would just kind of flip, so it would have a negative slope. The reason for this is because if you flip the axes, you're basically moving in the negative direction instead of the positive direction. So the velocity graph would still be a horizontal line, but it would actually have a negative velocity because of the direction. So what does it mean? So obviously it would be pretty difficult to determine like exactly how many forces are being added up to zero. Net force to zero net force. Friction, gravity, air resistance are all contributing factors, and there could be like more that we don't know about in this particular scenario. but identifying how much exactly each force contributes would be very difficult. For example, like friction could be have a really strong effect on the data, or could not have a big effect at all. Thank you.